Hello there. Bienvenidos. Bienvenidos a la clase de química. All right. So, ow. No pica. No love. So you guys get double the homework. All right. So, let's check this out. In this unit, we are going to begin talking about gases, right? And there's a lot of math that's involved with gases, but we're not really going to focus on that today. Today, we're just going to understand one of the variables, right? One of the things that affect gases, right? Now, when studying gases, you have to make a lot of assumptions. The idea of the atom is that it's a tiny, tiny little particle. Well, if you're trying to explain like the air around us, it's complicated. It's very, very complicated. Imagine describing the ocean. Think of how difficult it is to describe the ocean with like all the currents that are involved, and that's something that we can visually see. So with gases and studying their behaviors, we have to make a lot of assumptions. We have to make the problem simpler so that we can explain any patterns and understand them. All right. So one of the first things we're going to talk about is gases and how they work with volume. So gases fill up their container. They like to spread out to fill up their container, and they do it in a uniform pattern. It's the same throughout. Now, later on, we're going to talk about the motion, the kinetic molecular theory. But gas particles like to move in straight lines. Everything likes to move in a straight line until something gets in the way. That's Isaac Newton, right? So, right here, imagine the gas particles are moving in a straight line, and then eventually they crash into something and they change directions. But they always move in straight lines. And as time passes by, the gas particles fill up their entire area. All right, and they move in straight lines until they crash into something. Now, the number of collisions, or how frequently these gas particles hit these walls, will increase the pressure. And there's multiple ways that we can increase the pressure. All you have to think about is what ways can you increase the number of collisions inside the container? What can we do to this to increase the collisions? Well, one, we can make the particles go faster. Well, how do we make them go faster? You can heat them up. You can add some energy. So now they have more kinetic energy, so they begin to crash into the walls faster, and you get a higher pressure. So there's a relationship between the temperature and the pressure. All right, now maybe if we start over again because I got a little too crazy. All right, but go. Now, there's a relationship between temperature and pressure. But there's other relationships as well. For example, you can increase the number of collisions not by opening it, but by actually reducing the volume, making it smaller. You can see what will happen to the pressure as we close the container. As we compress the gases, they crash into the walls more and more and more, and you have a higher pressure. So pressure is the collisions caused by the particle motion, right? You can just keep going. Now, and one of the reasons why you ever see like an aerosol can or like a spray of some sort that says do not, it says contents under pressure, do not place in direct heat, because if you add heat, well, the pressure will go up really, really fast and things will go kaboom. So be very, very careful and read directions. All right. So that tells us, that tells us that there's a relationship between pressure and volume. All right. Now, there are other things we can do to increase the pressure. We can keep adding more particles, right? So if you So there's a relationship between the pressure and the moles of the gas involved. All right, so the number of gas particles will affect the pressure. So since you see all of these relationships, you know that you can predict future relationships as well. So that's where the gas laws are going to come in, and they're very, very important. Now, let's talk about the barometer. Oh, I think I shake my... Every time I erase, the screen shakes. My bad. I gotta fix that. All right, so the pressure, let's check that out. Well, how was pressure even measured? Why does it say ATM? Well, ATM is the unit of pressure for atmospheres. And then kPa is a kilopascal. Pascal was a scientist that was... I actually don't know much about him. I should look into him. But anyways, let's talk about how pressure is measured. A very common way of measuring it is millimeters of mercury. Now, there is a few unit conversions you must know. For example, 760 millimeters of mercury is the same thing as 760 torr. Torr was an Italian scientist that studied pressure, so he got a unit named after him. Torrellini? Or is that a pasta? Anyways, is that racist? I'll shut up. I'll shut up. All right. And 760 millimeters of mercury is what we call 1 atmosphere, which is the same thing as 101,350 pascals, which is, I think there's a 1 after that, but I'm not going to check right now. The same thing as 101.350 kilopascals. So you're going to have to know these units, and you should be able to interchange between them. So all of these are equal, by the way. So in the future, you can make a conversion factor with any of them on top and the other on the bottom. It doesn't matter which. Okay, now let's talk about how pressure came to be measured. Right, this right here is a barometer. And how does a barometer work? How does a barometer measure the pressure of anything? Well, the air particles, right, everything around us is pushing down. So right now there's air pushing down on you. There's air pushing down in your ears. There's air pushing down your shoulders, your eyes, everywhere. Everywhere. Sometimes those changes in pressures are what causes our ears to, pop. But the particles, the air particles are pushing down onto this thing of mercury. And if the pressure increases, right? Let's say the temperature gets hotter, so the gas particles are pushing down further. Well, the mercury is going to push upwards. All right? So, and then the distance, see, the erasing. The distance from the tip of where the mercury is at to where the bottom, measured in millimeters, will give you your pressure. So you get like a ruler and you go to the little line side, the non-American side. You can measure the millimeters right there, and that's how pressure was measured. It was just measured as a distance, the amount that the mercury gets pushed. All right. Now, that right there was used to calculate the pressure of the atmosphere. If you were to go to a very cold place, or maybe if you were to measure it at night, right? Let's say nighttime comes. Well, the gas particles aren't moving as much because the sun's not out. They don't have as much energy. They're cooled down. So they're not going to push down as hard. And as a result, the mercury won't go that high. So the millimeters of mercury is going to be lower. It's a lower pressure, right? Now, let's take a look at a J tube, right? A J tube is what Robert Boyle was one of the Oh, he made a bunch of contributions, all right, to science. Um, Super smart man. Super smart man. Now I think he was one of the first. He was along. He was during that time in history where record keeping was like, you know, starting to become the standard. He was one of the first to set the standard alongside Lavoisier, Newton, and all those smarty pants. All right, so how was this instrument used to measure? Well, they had already learned to isolate gases, right? So he would fill these things up with different gases. So with pure oxygen or pure nitrogen, and he would be able to isolate them. And then he'd pour in some mercury, and the mercury would push the gas up to a corner, right? It pushes the gas up to a corner. Now, those gas particles will push back, right? They will push back and they'll create this distance. And that pushback is the pressure of the gas. So they know that, well, he knew that the room temperature was 760 mmHg. And through those ways, he was able to determine the pressure of the gas. So now he tried it with a bunch of different gases, and he realized that the number of particles, well, Avogadro noticed this actually later on, but this experiment eventually led to the assumptions we make today. We assume that all gas particles are the same, that no gases are different because of the data that was gathered. It just showed that nothing else really mattered, that it didn't matter what gas it was made out of. The amount of particles is what really mattered. That's something that Avogadro came up with later. All right, so I believe you have like some problems with this. Let's check it out. It's just conversions, but I really wanted to give you guys an understanding of pressure and where it came from. If I forgot something, well, we'll talk about it later. But let's see. Oh, it seems like you guys have to write some stuff down. Oh, these problems, converting from units to units, right? That's not bad. That's easy peasy. Did I already have that thing written out? Yes, we did. Let's delete some of these. Whoops. All right. So, if we have 3.5 ATM and we want to convert it to, what was the problem? To the 4 other units. Oof. I'll convert it to 2 and then I'll say peace out. All right. So 3.5 ATM is the same thing as a 1 atmosphere at the bottom, and we'll turn it into mmHg. All right, and we'll do the same thing, and since I'm lazy, I'll turn it to torr. No, I won't turn it to torr. We already know what torr is, so let's not waste space. Let's be efficient. Let's turn it into 101 350 kilopascals, and that's the same thing as 1 ATM. So 3.5 ATM. I need to not shake. Oof. Sorry, that's my washing machine. Okay, so 3.5 times 760. You do it. Have your calculators out. Don't be like me. So we have 2,660. Pretend that's a 0. mmHg. So now we have millimeters of mercury. And then over here, we do 3.5 times 101,350. That gives us 354,725 kPa. All right, now let's turn it into other units. So turning it into torr is really easy. And then turning it into, oh, sorry, this was in kPa. This was just regular PA. I was getting ahead of myself. I'm so sorry. But to turn it into kPa is very simple. Hello, why can't I write? Oh, there we go. So it becomes 354.725 because kilo is 1,000, right? So we're moving the decimal 3 times because we're dividing by 1,000. So 1, 2, 3 gives us. So here we have 4 different units. I only wanted to do 1, but you're welcome. All right. That's kind of it for these. We'll talk about the data that I was referring to using the. Oh, it crashed. Perfect. Hello. Using the JTube. All right. So using the JTube, that data, we'll actually use it. So see you later.